Hello, I'm 𝗀𝘁 from Seoul National University presenting effective zero compression on ReRAM-based SparseDNN accelerators. This work is done with my colleagues at Seoul National University and my advisor 𝗔𝗯𝘀𝘁𝗁. The first two authors contributed equally to this work. Neural networks are heavily overparameterized. Therefore, a large portion of DNN weights can be zeroed out without significant accuracy loss. Moreover, many applications require lightweight networks due to space or inference time constraints. According to the pruning granularity, network pruning is divided into three types: unstructured pruning, block-based pruning, and structured pruning. Unstructured pruning can achieve high accuracy on target sparsity or high sparsity without significant accuracy loss. However, resulting weight matrices are sparse, which cannot lead to compression and speedup without dedicated hardware and libraries. On the other hand, for structured pruning, no dedicated hardware and libraries are required to realize the benefits while having relatively low sparsity. On the hardware side, ReRAM crossbar array can perform in situ multiply accumulate operation by applying voltages on multi-word lines at the same time. When voltage V1 and V2 is asserted to the first and the second word line respectively, the resulting current at the end of the bitline is equal to V1G1 plus V2G2, which is the dot product between conductance vector and input voltage vector. Extending this concept, n by n ReRAM crossbar array can act as a matrix vector multiplier to execute the matrix vector multiplication. For DNN operations, weights are programmed as conductance of registers, and input activations are applied to each word line as a voltage source. Now, I show how to map the filter weights to a crossbar array for a convolution layer. Assume that there are weights of two filters as shown in the figure. First, a weight of 7 on filter 0 and a weight of 15 on filter 1 are mapped to the first word line, considering the 4-bit precision of the weight and the 2 bits per cell of ReRAM in this example. Afterward, weights in the same position of the filters are mapped to the cells in the same word line in order. One constraint of the ReRAM crossbar array is that it must be activated at a small granularity called operation unit due to reliability concerns. For example, as shown in the figure, a 4x4 array consists of 2 OUs with 2x4 cells per each, resulting in 2 cycles to execute matrix vector multiplication. A recent work, Sparse ReRAM engine, proposed an OU-based row compression, which compresses 0 weights if all weights in a row of an OU are 0. However, it means that row with both 0 and non-zero weights cannot be compressed. For element-wise pruned networks, the positions of the 0 weights are irregular, so that many of pruned weights still remain on the array even after OU-based row compression is applied. So, is there a better way to make more all-zero rows? To deal with it, we proposed 2 key techniques that increase opportunities for row compression at OU granularity on ReRAM-based DNN accelerators. First, we introduce OU-wise mapping strategy, which produces more all-zero rows in OU, and thus improve the compression ratio. Second, we propose the recovery of uncompressed 0 weights, which can improve the accuracy under the fixed compression ratio. Before diving into our techniques, I will introduce a little background for better comprehension. In this example, I will show Naïve weight mapping. For convenience, a weight is displayed as weight mask, not weight value, which means that 0 indicates pruned weight and 1 indicates survived weight. In Naïve weight mapping, weights of its filter are mapped to the array in order and from the OUs. Here we assume the size of OU is 2x2, which means an OU contains 2 weights for each of 2 filters. If applying the ORC on the Naïve weight mapping, for the same weight mask, 3 ORC operation occurs, and the remaining weights are mapped to the array and form the OUs. Here we can see the number of OU is decreased from 8 to 7 with the help of ORC. Now, I will introduce our first technique, OU-wise mapping strategy, which can further improve the weight compression. OU-wise mapping strategy is divided into 3 steps. Step 1 is filter reordering, Step 2 is compression and OU mapping, and Step 3 is array mapping. With this strategy, we can achieve relatively high compression ratio. Step 1. Filter reordering. First of all, we set the base filter and search the pair filter to form an OU. Since in the beginning, all weights of filters remain unmapped, we set filter 1 as base filter. Afterward, we greedily search the pair filter that yields the highest compression ratio. If filter 1 and filter 2 are paired, there is no compressed row while forming the first OU. Now, to pair the filter 1 and filter 3, we reorder the filter. For the pair of filter 1 and filter 3, still no compressed row. If filter 1 and filter 4 are paired, 2 rows are compressed. Therefore, we pair the filter 1 and filter 4 to form the first OU. Now we obtain OU1. For the remaining weights, we repeat the same procedure. Now we set filter 2 as base filter, since filter 2 and 3 have the most number of unmapped weights. Now we find the best pair of filter 2. Pairing filter 2 and filter 3 yields one compressed row, which is the most. Therefore, we form the second OU with the weights of filter 2 and filter 3, and we obtain OU2. Keep repeating the same procedure. Set filter 2 as base filter, and find the best pair of filter 2. Now we select the filter 4 as pair filter, and OU3 is obtained. Finally, filter 3 and filter 1 are paired, and make OU4. After repeating step 1 and step 2 until all the weights are mapped to the corresponding OUs, we map the crossbar array with these obtained OU maps. The OU map is stacked until the first array is full, and then the remaining OU map is allocated to the next array. Since we stacked the OU maps into an array horizontally, each column has balanced number of weights mapped on the array. Now, I will introduce our second technique, recovery of an uncompressed zero weight. After compression, even utilizing OU-wise mapping strategy, there still remain zero weights that are pruned but not compressed. Since we know the exact position of the weight mask for those weights, we can recover the mask of the weights. Then, for the same array compression ratio, we can lower the sparsity and thus get higher accuracy. We evaluate the efficiency of our scheme by estimating the compression ratio and model accuracy on various sparsity, and measuring the storage overhead for indexing and the energy consumption. We compare our evaluation result with the baseline, which maps all weights into the array without using any compression, and SRE, which utilizes OU-based row compression with Naïve mapping. We also compare our result with SRE 1x2, which uses ORC on 1x2 block pruned model. We assume a generic ReRAM-based DNN accelerator and use 2 bits per cell and OU size of 16x16 for our evaluation. Both inputs and weights are quantized to a 16-bit fixed point format. We built a custom simulator and evaluated 3 DNN models on Cypher 100 dataset. The proposed weight mapping scheme effectively eliminates redundant weights in the crossbar, and the zero weights recovery scheme allows for better accuracy at the same compression ratio. Overall, the proposed scheme achieved 3.27 to 4.26 times array compression ratio with negligible accuracy loss over the baseline. Before showing the storage overhead, I will show what kind of indexing is necessary for each case. For Naïve mapping, all the weights are mapped to the array without compression. Thus, input activations are fed to the corresponding rows in order. In addition, since filter reordering is not applied, an output from each column shows the result of each filter. Therefore, we can just deliver the outputs to the corresponding location of the output register in order as well. When the ORC is applied, since we compress some rows with all zero weights in some OUs, proper input activation should be fed to the wordline in order for the calculation to be correct. Thus, input indexing is needed. Lastly, in our scheme, in addition to the ORC, filter reordering is applied when forming the OUs. Therefore, to correctly deliver the outputs to the corresponding location of the output register, output indexing is also necessary. Here, the storage overhead is shown in the figure. Compared to SRE, our scheme needs equal or smaller storage overhead, even with additional output indexing. This is because we eliminate redundant mapping with better compression and map a smaller amount of weights than as SRE, which means that the number of OUs is fewer than SRE. Overheads of the input and output indexing are proportional to the number of rows and the number of filters in OU respectively, and we adapt practical values for those numbers, considering bit precision of the weight, bits per cell, and the size of an OU. As mentioned, with our effective weight compression, we map fewer OU maps and use fewer arrays. Therefore, our scheme requires fewer cycles and thus less energy. Even with additional index buffers and decoders, we consume only 0.25 to 0.32 times energy compared to the baseline. Conclusion. We propose a novel weight mapping scheme that better exploits weight sparsity on ReRAM-based DNN accelerators. The first technique, OU-wise mapping strategy, improves the compression ratio, and the second technique, recovery of uncompressed zero weights, improves the accuracy of DNN models. Overall, we achieved 3.27 to 4.26 times array compression ratio compared to the baseline ReRAM-based DNN accelerator. Thank you for listening to our talk. Please refer to the full paper for more details. Thanks.